All right, kids, so here we go. I am in my den today. It's been a long time since I had a picture. I'm wearing my science t-shirt, and in honor of April the giraffe, I took the giraffe picture in the background. I believe my son Vincent did that one. So there it is. We're talking about gas laws on this one, and in gas laws are going to assume the kinetic molecular theory is in effect. And what that says is that all matter consists of tiny particles in constant motion. And this theory assumes the following about gases. Particles in a gas are considered small, hard spheres with negligible volume. So they don't take up a lot of space, but they're small and hard. You know this if you see a gas, right? You don't really see a gas, but and you can walk through it without having little things hit you. So there's not a real volume, but when they collide with each other, there's actual hard spheres. The motion of these particles is rapid, constant, and random, and all collisions between particles are perfectly inelastic like billiard balls. No energy is lost. And I have this GIF that did not work. So just very quickly, let's go to the GIF that did work. Let's go to that GIF that did work. Where's my GIF that did work? Oh no, I can't get it. Oh wait, there it is. All right, this one. So here is a GIF of a billiard ball situation. Not so sure that's real. Those balls seem to be moving pretty good for that may not be inelastic. Anyway, all right, back to the show. So now this is some of the more intuitive things we've done all year. Pressure, the force exerted by gas on a surface, we're going to call that basically collisions, okay? Those are the particles colliding with the surface. That's what causes pressure. Volume is the amount of space occupied by something. We're going to just call that one word, space. Temperature, the average kinetic energy of particles. Average kinetic energy is mass times velocity, 1/2 mv squared, but we're going to just call it movement. Temperature is movement. And we actually gave these abbreviations: pressure P, volume V, and temperature T. Pressure is the big problem with this one. It's in atmospheres, kilopascals, millimeters of mercury, or torr. Millimeters of mercury and torr are the same thing. It's 760 of those equal 101.3 pascals, which equals 1 atmosphere. Liters is the volume. Celsius is temperature, but we convert it to Kelvin for everything we do with gases. Kelvin does not have degrees because it's absolute. Why is it absolute? Well, because the temperature we typically measure in Celsius convert to Kelvin, and the Kelvin scale is based on the notion that at 0 Kelvin, absolute zero, particle motion ceases. And that was a GIF at one point that worked, where these particles here are moving and these are not. And because they're moving, they make the thermometer go up higher. So that is the deal with that. So basically, if I can, and I will, this all looks like what we did in class, right? Here is a gas, and the gas is moving around, random motion, colliding into things that causes pressure. And we can mess with the volume V, we can mess with the temperature T, and we can mess with the pressure P, basically with the volume and such, and the temperature affect the pressure. So the first part of what we did deals with no change in the amount of gas. So by the way, so Kelvin absolute to zero is 0 degrees Kelvin. It's minus 273 Celsius. There's no motion. Conversions. So 100, I'm going to try this with my pen on an angle. Let's see. All right, so 100 degrees Celsius is 100 plus 273. 270. So that equals 373 Kelvin. And minus 23 plus 273 would therefore equal 250 Kelvin. 250? Yeah, right? 250 Kelvin, yes. So that is how you do those conversions. You just add 273 to Celsius and you get the Kelvin. STP, standard temperature and pressure. That is, if you had to guess, if you really had to think about it, and you will need to know this, but I already just told you last slide, 273, right? That's the number you have to remember to convert things to Kelvin. So that's why they set the temperature at 273 Kelvin. It's the same number you have to remember, and you're done. I will give you these conversions for pressure. 1 atmosphere equals 101.3 kilopascals equals 760 millimeters of mercury, which is also 760 torr. So you're going to need to be able to convert these things. And the key here is that all units must match when we're doing these problems. If you go in with kilopascals, you come out with kilopascals. And if you go in with atmospheres, you better come out with atmospheres. Just make sure you keep that all straight. So if we had to convert 123, am I on pen? I am. So 123 kilopascals. If we had to get from kilopascals to atmospheres, we would just use this conversion right here. So 1 atmosphere is equal to 101.3 kilopascals. And we would divide that by, so 123 divided by 101.3, and we get a syntax error. That's what you get. 123 divided by 101.3, you get 1.21 atmospheres. So that would equal 1.21 atmospheres. Kilopascals cancels. Hopefully you're used to that by now. So you will need to know how to do some of that. But this all boils down to the combined gas law. And the combined gas law relates pressure, volume, and temperature for an enclosed gas. So again, like what I just showed you with the interactive, you calculate when the amount is held constant, and that is P1 V1 over T1 equals P2 V2 over T2. And please remember, I was trying to establish a divided sign, so that's not some weird sign you haven't seen before, but a divided sign. Hopefully you realize that by